Evening, everyone. I'm Jelle Verest. I'm currently doing my PhD project at the Eindhoven University of Technology. I'm going to present part of my master's thesis on RFIC design using Skywater. And I'm now currently continuing this as a hobby project. So, first off, I think we can all agree that Skywater has been a huge success. It has driven so many open source and new projects. Many people who would otherwise not be involved are now actively doing IC design, which is a major win. I've even seen loads of YouTube videos of people getting into IC design and doing this, doing a tiny tape out first and just documenting their entire process. So it's beautiful to see. The only thing is that this is only digital, or mostly digital and hardly any RF. And I'll be showing you a bit of the challenges that are involved with that and the reasons why that is. And then hopefully I'll present also a bit of some small solutions. So, first off, I'll be talking about the transistors. It's vital to know what we're working with, how fast they can go, so I'll be talking a bit about that. After that, Matt Van also already said that there's no noise in the PDK currently, so what I'm going to be talking about is a way to mitigate this. Afterwards, I'll be talking a bit about inductors. Inductors are a vital part in RF designs, and currently there's no standard way of doing inductor design. And then lastly, I'll show a proof of concept VCO. So first, the transistors. What we want to do is we want to characterize them in terms of speed. Now, how do we do this? We make an amplifier out of it, and we look at the gain. What we see is if we increase the frequency, the gain will lower up till a point where it's 1. And that's exactly that crossing there. And what we can do is, this is the frequency that we will be using in characterizing a technology. We can do this with current going in and current going out. This way you can get something that is called the transition frequency, FT, or we can do it with power, and that is called the maximum oscillation frequency. If we now look at the fastest transistors that are available in this PDK, you can see those in the fat blue line there. And what you see is they're rather optimistic. They do fall broadly in line with other processes, but it's still quite optimistic. And coupled with some other things, if we look into the layout, what we see is that this is the layout of an RF transistor, and we immediately spot some peculiarities. We don't have a guard edge protecting, lowering the amount of noise. We have huge plates which increase capacitance, and so this nice picture of a high FT and Fmax is probably not true. We do have these standard transistors, these low frequency, and they do have a guard edge. In my design, what I did is I used the RF models. These perform worse than the baseband models, but then I used the baseband in my layout. So, having covered that, we will be talking about noise as well. See, there is simply no noise, but can we boil it down to some type of thermal noise? In the case of a voltage controlled oscillator, a VCO, that is possible. See, say I have a voltage controlled oscillator and it produces this output wave. If I then inject a charge into a certain point in time, right there, well, what then happens is this charge is absorbed by the capacitances in this node, and the voltage will increase. This voltage will then induce a phase shift. This phase shift can be measured, can be plotted, and what we can do is, if we do it over various points of time, we find that we have an entire function which describes the the charge injection at a certain point in time to the phase change. This is called an impulse sensitivity function. This impulse sensitivity function is, it turns out, is enough to get a good approximation for noise in an oscillator without knowing anything about the transistors. And then we have covered the transistors, we've covered the noise. Now onto the inductors. What can we do? We need both a good layout editor and an EM solver. For the layout, I chose K-layout. It was just very simple to create a parameterizable cell, a P-cell macro, and then use that. Then for the EM solvers, what I did is I found the fast field solvers suite. This is a set of multiple different partial EM solvers, which one will find the inductance and the mutual inductance, the resistances, and one other will find the capacitances. So what I did is I created a P-cell, I made this inductor, and afterwards I made a script, GDS to fasthenry.py, and what it does is it converts this GDS layout to a set of nodes with vertices between them. And this is what the format that Fast Henry, the inductance solver, is using. And I can feed it into there, and what I get out is a nice SPICE file with the equivalent model. I can arbitrarily choose the amount of poles, but for this, I thought a simple, just one simple inductance might suffice. Then I did the same with FasterCap. FasterCap is the same, but it gets the capacitance between different points. And so I used a triangulation to convert it into triangles. That is then read by FasterCap, and out comes a Maxwell capacitance matrix. This Maxwell capacitance matrix I can reverse into the capacitance between different nodes. Now what we can do after this is we can combine these two together. This is still a work in progress, and I haven't written an automated way of doing this, but it will be coming soon. And from that, you can simply import the SPICE file into your circuit simulator of choice. Then, lastly, I've made a proof of concept VCO. These are the specs. It's a 10 gigahertz center frequency VCO. It's a simple LC oscillator, just using NMOS. It's not all that important. The most important part is that what we have here is a cloud of the literature of other 130 nanometer VCOs. And where the blue are CMOS, the red crosses are BJT VCOs, and the yellowish point is this work. And what I want you to see is that although, what I want you to see is that these are all the points, the results are fit nicely within the trends that we find. First off, the tuning range, then the impulse sensitivity function. What I did is I injected current during a transient simulation, injected currents at various points of time and constructed the dashed yellow line from there. From this, we can find the phase noise, and here the phase noise, what you see is it increases with center frequency, and I'm nicely somewhere in the middle. As well, figure of merit, right around the same. And so what you can see is that this behaves like a standard 130 nanometer VCO. Keep in mind, this is has not yet received a tape out because there wasn't any time during my project to do this, but it is nonetheless still planned, and hopefully I might be able to present this next year. But that's about it. I tried to show you in this very short presentation what the capabilities are and what the challenges are of RFIC design in Skywater. And you see here a QR code to my GitHub page. And lastly, what I hope to have shown is this is basically the end of what we can achieve without a tape out. After this, we simply need to measure, and then we can finally find some good answers. Thank you very much.
Yeah, so just I would like to have your opinion. Currently, I'm using in my organization a multi-channel DAC that runs between 100 megahertz to 2 gigahertz range. And the only option I have is an RFSoC from Xilinx, right? It each board cost me 20,000 euros around, right? Do you think that with this Skywater 130, based upon your work, any solution in this range would be commercially possible going ahead? Just your opinion, maybe.
Well, what we would need is more detailed models of the FETs, and when they're well characterized in this region, then we can look into then we can finally say if this technology is capable of doing such a thing, because you will always have some requirements, and I don't know what they are and if that's possible. But if you find something, if you are able to test, to measure all these high frequency behaviors, then we might be able to figure this out.
Yeah, I have a question. So when I was doing the Chipalooza challenge, we had a number of circuits that were oscillators, and one of our specifications was for phase noise, and then people were coming back to me asking, well, how do you measure phase noise? Because ngSpice doesn't have a phase noise analysis. And your method looks like it is possibly generally extensible. Do you have that? Is it generally extensible, and do you have it published somewhere?
Yes, it's based on it's not my own work, but I wanted to show it anyway to give a bit of the context. This is fully the work of Ali Hajimiri in his I believe 91 publication on low noise oscillators or something like that. I believe it's his PhD thesis. It's a really good read. It's all about not seeing an LC oscillator as a time invariant system, but as a time varying system. From there, you can see that at some points in time, an oscillator is more vulnerable to noise than at other points in time, and it can generally be well approximated. The phase noise can generally be well approximated using this method, and then relating the whole circuit back to the thermal noise of one equivalent resistor.
I've got a question. Is there a way of characterizing this with the low bandwidth I/O cells that we have on the pad ring? Could we implement a divider to see something, or put a gigahertz signal out, and even though we've got only a 50 megahertz bandwidth, still see something? How?
Yeah, that's possible. It's now a colleague of mine has the same problem. He's working on 140 gigahertz radar, and he doesn't get it through the bond wire. So what he does is he has two signals and he mixes them together, so you get a low frequency component. And that low frequency component, after doing some math, you can see what the original function is, what the original signal is, if you know also the reference.
More questions?
Thanks for the talk. So basically you were using your estimation of the phase noise to size the transistors in the end?
I am not really. What I'm doing instead is I just wanted to have a proof of concept, so a working VCO, and see what the general phase noise would be. This obviously is not going to be 100% accurate. It's most likely not even going to be all that accurate, because there is this makes the assumption that the transistors are well suited, well optimized for this RF. So we might need to multiply. We might need to add a couple of dBs extra, but that's basically it. Yeah.
More questions? If not, let's thank the speaker again.